happen again here because I think there was a ground loop through the projector here. You are totally right. So first of all, thank you very much for this invitation. It's a great honor speaking here, and I wasn't really sure, what the best title of my talk should be. And one of them could have been, BFLs, and I don't know whether you know what that stands for. I will not. I think we need to adjust the size here again. But anyway, so there we go. So I'm going to talk about next generation scientific lasers, which is something which we're developing at Lawrence Livermore National Laboratory. However, a lot of these start to actually have an impact for commercial applications, so it might be interesting for you. So there are actually two big lasers under development right now at Livermore, and both of these lasers are major short pulse laser systems, and everything what I refer to as short pulse is in the picosecond regime or less, so down to hundreds or tens of femtoseconds. And so the lasers which we're building is the advanced radiographic capability, which is depicted here on the left side, and the high average power petawatt laser system, which is called APALS. This one we're building for the extreme light infrastructure, which is a $1 billion actually endeavor in Europe right now. And it will be the highest repetition rate petawatt laser system, so we'll produce 10 to the 15 watts in the near field and focused up to 10 to the 23 watts per square centimeter. Was way too high for material processing, but we can do other exciting stuff with it. And this one is going to be the most energetic petawatt laser system with up to 12 kilojoules with 30 picoseconds. So very different laser systems than what we heard before, but let's see what we can do with those. So just show you where I'm at home. The Lawrence Livermore National Laboratory is about a 50-minute drive, and traffic takes a bit longer from San Francisco. It's equally far from the Silicon Valley. It was established in 1952. Its main mission is national security. And we have about 6,000 employees, of which about half of them are PhD engineering or physics or chemistry or scientists. Our annual budget is about $1.6 billion. So Livermore has pioneered actually quite a number of photon delivering systems. It started a long time ago in the 60s, just briefly after the laser was invented. They started actually building laser systems for inertial fusion. We built the Nova Petawatt, as you probably remember. It was the first petawatt laser system in the world. It was based on the Nova system, which was the predecessor of the NISH, the National Ignition Facility, which is today the highest energy laser system in the world. It delivers up to 4 megajoules in the infrared and about 2 megajoules in the blue. DPAL is a CW laser system. Mercury was the world's highest pulsed average power laser system. It's not any longer because you will hear this later. The heat capacity laser is tens of kilowatt system to hundreds of kilowatt laser system, which we built also for defense purposes. T-Rex is the world's brightest laser gamma source. And ALICE was a system for actually isotope separation for uranium, and it was the highest average power tunable laser system, which was built a few years ago. And so the new ones which we will be talking about today is APALS and ARC. So NIF, for those of you who are not familiar with this, NIF is a laser fusion driver, actually. Its main purpose is to generate extreme states which are similar in the side of the sun or an exploding nuclear weapon, and to study those. And so there's the ignition campaign, which is basically depicted here on the left side, and then there's also a study of materials under extreme conditions, very, very high pressures and so forth, which occur in nuclear weapons, but also in planets, suns, and so forth. This shows the target chamber here, and you can see, this is 192 beams actually. So this is 96, but there's another 96 from the bottom. There's 192 beams totally going into this target chamber, and they're focused down to 1 millimeter into a little capsule where we then actually generate these states. Peak power is about 0.5 petawatt. And the goal is actually to generate a mini sun on Earth. So this shows the sun here. And what we're trying to do is actually ignite and do the same process, which is actually powering up the sun. You can see here is a comparison for the states of matter which we can generate here between NIF and the sun here. And you can see, basically we can get matter to the same temperatures here. We can get it to similar densities here, and drive very, very high pressures, which is the hundreds of gigabars here. So when you actually drive these matter to extreme states of very high compression, which is about 1,000 times solid density, they become very opaque, and there's just impossible to actually look through them and see what's happening inside. In order to understand actually inertial fusion and what's happening in the target, you actually have to look through and find out what's in there. And in normal X-ray sources, so forth, doesn't work. The other thing what you need is you need a very fast X-ray source with very short pulse duration, because these states only last for tens of picoseconds or so forth. So it's very fast motion. And so the common way to do this is actually use a high-intensity laser to drive a very intense X-ray source, a point source, in order to generate an X-ray pulse which can then look through the matter. And this is what the advanced radiographic capability is for. And so it will produce, on the order of 100 keV photons up to 200 keV photons for probing that matter. And it works relatively similar, like going to the doctor and getting your bones X-rayed. So here's a little movie showing you how it works. So we're using actually 4 of the NIF beam lines to amplify a chirp pulse, which is depicted here, and it's running ahead of the main drive pulses. So in each of the red pulses, there's about 30 kilojoules in the infrared. A little less here in the chirp pulse because it's much shorter, so we can't run it at high of the energy. You can see it's going through the amplifiers, now through the spatial filters here, and then it goes into the switch yard where it will be distributed. So first of all, we of course have to recompress the pulse. It's about a couple of nanoseconds long right now. It goes through a folded compressor design here. We're talking about 6 kilojoules here roughly, and then we go to the target. So let's slow down this a little bit. So we turned on the blue light, which is driven by the NIF. And for about 20 nanoseconds, we're heating this whole room. It's like an oven. And inside is a little DT capsule, which then gets baked in the X-ray oven and compressed through just the rocket effect. And it starts actually imploding. And so we generate very high pressures. And so now we want to actually see what's inside. And so now we have put a flax here, which is basically a gold target. And now you can see the very short arc pulses coming on there now, about 30 picoseconds short or even shorter. And each of them will hit one of these targets, boom, and generate an X-ray flash, which goes through the target. And you can see they're flying away because the target chamber is about 10 meters in length. It takes a while. And so you can actually get a movie out of this. And that allows you then to dynamically understand what's happening in your target. And so ARC is currently being ramped to its full performance. Today we're delivering about 1 kilojoule, and this actually shows you a picture here of one of the compressor vessels. It's very compact, about 5.5 meters in size, and we're passing several kilojoules through that. All right, now for something completely different. What if we make these pulses even shorter? And so if you look in the scientific literature, a lot of people are using X-ray-driven, laser-driven X-ray sources or laser-driven particle beams. And why are these interesting? So you can use relatively weak lasers to drive high harmonic generation in gases, so nonlinear effect, and you get kilovolts up to 1 kilovolt X-rays, but they are coherent, and so they allow you actually to do imaging, phase contrast imaging, and so forth, and so you can explore on the nanoscale molecules or solid state samples with very high resolution. And so there has been a lot of talk about this in the last couple of years. Betatron radiation is something which comes for free. It's basically when you wiggle an electron, you get also an intense X-ray pulse out of this, and we're generating the electron with a laser. You can also drive a neutron source or a proton source, which is interesting actually to detect nuclear materials from further away. You can drive X-ray lasers. You're probably familiar with that. Company radiography is just what we talked about. And then there's another one, which is particle acceleration, because you can not only accelerate electrons, you can also accelerate protons or other things, which then can be used for example, medical treatment, but also for scientific analysis, material physics, and so forth. Is very interesting. And the reason why this works so well over X-rays is because those protons or carbon ions, when they penetrate the tissue, they actually penetrate it, and then they come to a sudden stop, and that's where they deposit all the energy, which means like they kill really the cancer cells with like 100 micron precision or so forth. It's actually working really well, but we haven't demonstrated this with lasers yet. So how does this work? Actually, if you have an intense laser pulse with about 10 to 20 watts per square centimeter, which is the typical output of a joule-class femtosecond laser system, and you hit it on a solid metal, for example, you generate a plasma. Plasma means you separate the electrons from the ions, and then a lot of stuff happens. You drive extreme currents in there, you drive the electrons into the target, you generate a lot of Bremsstrahlung. You also generate EUV or other things. You get direct fusion through accelerated particles. You get a particle beam coming out here in the back from electrons, followed then later by protons through target normal sheath acceleration. You get fission, you get photofission, you get all sorts of stuff. And so it's really interesting working with high intensity lasers, and people have been very excited about this, using this then for applications. So let me just look at one of them. We have no time for actually going in all these details, but if you think about accelerators, which is something which people use for a lot of scientific, but also for a lot of medical applications. If you look at typical RF accelerators, there's a C-band accelerator here. This has up to about 100 GeV per meter. Actually, would be then in the X-band, but a C-band would be even longer like this and have like 10 MeV per meter in acceleration potential. So and that means like we come at some point we come to a stop, which means like we cannot accelerate faster because we get electrical breakdown in the RF structure, and that has been recognized by today's accelerator facilities that they cannot go higher because of that problem. If you look at a laser plasma accelerator, which is you generate a plasma, and you think about like you have a boat going through water, right? And if you look behind the boat, you see a wake. So you see two waves, which are running to the side, but you see a wake, which is in parallel behind the boat. And if you take a surfboard, you can actually ride that wave. You can sit on that wave, and that's exactly what's happening in a plasma. You send a short laser pulse through a plasma, through a low-density plasma. It generates a wave in there, and electron gets trapped on that wave, and they start surfing that wave, and they get accelerated. And you get up to 100 GeV per meter in field gradient for acceleration. So it's super interesting to use that because you can shrink, for example, the SLAC, which is like a 3 kilometer long accelerator, into a few centimeters here, which is shown by my colleague Wim Leemans from Berkeley. So the Department of Energy has recognized that need, but the problem is lasers are not there yet. There have been done proof of principle experiments, but the lasers don't provide mainly the average power and repetition rate and robustness which you need actually to drive this commercially. So if you look, on an energy per pulse duration plot, you get pretty much two sets of laser systems. There are the high field there's the Ti-Sapphire systems, which are depicted here in purple, and then the glass laser systems, which are depicted in red. And then a few are like OPCP and other systems. And the physics are here, high field physics. That's where you want to accelerate and so forth. Ultra fast is just very is mainly biology application. Then you have material physics application, which need a lot of energy, and that's why you see also here in the HED, high energy density physics and inertial confinement fusion. That's where the NIF lives up here, and these are basically fusion laser system. Now, if you look in the industrial application, they're down here. But let's look at the real applications, which is if we plot energy versus repetition rate. And so now you can see that all the commercial applications, positron emission tomography, electron acceleration here, neutron radiography, hadron therapy, that's cancer therapy, they sit roughly here. And there is almost no laser actually which makes it into this field here of kilowatt to 10 kilowatt of average power. The APALS system, which we're going to talk in a minute about, is the first laser which starts actually approaching that limit here. And so the European community actually has recognized that this step from proof of principle to real applications has to be made and has to be sponsored. And so they proposed a new project which is about $1.2 billion in funding, and it's across entire Europe, and it's called the Extreme Light Infrastructure. It's placed at 3 places. One is in Romania, one in Hungary, and one in the Czech Republic. And the Czech Republic actually contracted with us for the delivery of the high repetition rate advanced petawatt laser system, which is going to be their workhorse. It's a 10 hertz petawatt laser system, which turns then these proof of principles experiments into potential industrial applications. So what we're doing here is delivering a 10 hertz, 30 joule, 1 petawatt user facility. It's a 4-year project, and we're building it in Livermore, and then we ship it over there. And the reason why they contracted with us is because of the vast experience of Livermore in certain lasers. We talked about this before. It's the fusion laser systems, which are along here. It's the high average power laser systems, which are up here, and it's the high peak power laser systems, which are depicted here. And if you take this all together, then basically this expertise, you get to these new diode pumped petawatt laser systems. System architecture is pretty straightforward. We have a short pulse arm, which is this side. It's based on Ti-Sapphire. It's pretty straightforward. A lot of these lasers do actually exist. However, this part does not exist, which is a high power, high average power laser amplifier, which goes to tens of joules with roughly about half a kilowatt output. And it needs to be pumped by a pump laser system, which is a long pulse laser system here, and that's actually where most of the technology development is, because it is diode pumped and it puts out 2 kilowatt of average power with 200 joules at 10 hertz. It's based on the NIF technology or NIF architecture. This is a picture here of the NIF system. This is about over 100 meter long, so that would be not very feasible. And it's based on flash lamp pump glass systems, and so with a shot rate of a shot every hour or so. So we need to do something about this. All right, so of course diode pumping comes to mind. The problem is that diodes don't, large diodes don't have the brightness, or didn't have the brightness for a long time, because you need about 10 to 15 kilowatts per square centimeter to pump neodymium glass. The advantage, of course, is if you take diodes, you don't have to remove as much heat. This is pretty straightforward. So if you do the math, actually, for a Ti-Sapphire system, you need about 154 kilojoule per petawatt, or 12 kilojoule per petawatt if you need a diode, if you use a diode. So if you run a 10 hertz system, which we saw is approaching actually the commercial application market, you would have to have, about a 2 megawatt facility, 2 megawatt power plant next door to drive that laser, while here you need only 150 kilowatts. The big deal, of course, is how you remove the heat. We have different technologies on the market. Rod amplifiers we're all familiar with. Problem is the stress pattern is perpendicular to the beam propagation, so you get lots of aberrations and stress birefringence. So it's not feasible. You just can't get the heat fast enough out if you scale this up to high energies. Thin disk, great technology, very consistent with rep rate and high average power, but not consistent with a lot of energy because you can't store a lot of energy because you run into the ASE limit at some point, and the disk has to remain thin. And then there's the multi-slab technology, which basically slices up a rod amplifier, but you cool basically in between. So the stress pattern is in the direction of the laser beam, and so you don't get those stress effects which cause aberrations. This has been pioneered before, or actually proposed already by John Emmett and Bill Krupke in 1984. They wrote a nice report on it. It is available if you can go and actually find it online. And so here's what we do. We take the NIF, we remove the flash lamps here, we shrink the amplifiers to normal incidence, we move the spatial filter out here and the polarization switch to a low fluence area because Pockle cells, of course, are sensitive to high fluence. We fold the system, and you have a very compact system. The other thing what we do is actually put a 90-degree rotator in there in order to compensate the birefringence, which always comes when you go at high average power and thermally stressing your material. Okay, so if you look at the candidates of materials you can use for a gain, I don't want to walk through the entire table here. It's in the literature. So if you compare ytterbium YAG, for example, with glass, or ytterbium SFAB, which is something, strontium fluorapatite, which is what we used in the Mercury system, is very attractive because it has a long lifetime of about a millisecond, so it's very nice for diode pumping. But unfortunately, no one makes it anymore, and so it's not easily available. If you look at ytterbium YAG, actually to get to ytterbium YAG to conceivable gain and energy storage, you have to cryocool it to about 100 to 200 Kelvin. And that's actually the difficult part about this system because you have to make your coatings consistent with that, and you have to keep it clean. And you have to manage, of course, amplified stimulated emission. Anyway, so if you look here, there is the other advantage is, of course, thermal conductivity, but the problem with ytterbium YAG is that it is not available in large sizes, and so people have started going to ceramic YAG, but the properties of the materials and the quality of the materials are, for large amplifiers are yet not good enough. Also, if you look at this plot, which is the efficiency of the laser system, that's the total efficiency, electrical efficiency for the diode power installed. And this is an example here for a fusion laser system, but it's directly applicable to APALS, or the smaller systems here. If you don't get your cooling right, if you look here in the efficiency for glass, if you want a 14% efficient system, you need about 40 gigawatts of installed peak laser power here for a 2 megajoule system. With ytterbium YAG, you only get slightly better here. And so, in order to actually operate in here, you really have to look at your cooling of the material in order to get it efficient. So we went with glass. Glass is very well understood. We have a long history with glass, and we know how to do it and how to make it actually in large apertures with good quality. And this is how it works. We cut the glass up, we put it into what we call vanes. It looks like a wing, and we flow helium gas over these over these wings in order to extract the heat. The pumps come from the left and right, so comes the extraction beam. We do the same for the Thai Sapphire, which is a complete new thing. No one has done this before. Fortunately, you don't have to cut the Thai Sapphire in very thin slabs because of better heat conductivity, and so you need only a few slabs here and a few gas channels. All right, one other thing, of course, is in these solid-state laser systems is that you need relay imaging, of course, right, in order to suppress growth of aberrations and contrast fluctuations. And so if you use a normal spatial filter, of course, you know all that. You have a machining laser here, and so you will drill your pinhole so the laser just goes wherever it wants, and so you have to mitigate that. In order to do that, we came up with this following idea here. If you distribute the intensity over a slit, you reduce the intensity on your slit by a factor of 100 roughly, which means you don't have the problems with ablation anymore, and you can use this. So in order to do this, we took a cylindrical lens and a cylindrical lens here, and so of course you get relay imaging then only in one axis. But if you have another telescope afterwards, which is clocked by 90 degrees, you actually image the other direction. You can slide this on top of each other, and then you get a fully compatible spatial relay telescope, which is the same thing as a normal relay telescope, but with reduced intensities here on the pinholes. And so that works too. We have built this, we've commissioned it, and we tested actually up to 300 joules per square centimeter on the slits, and it works perfectly. So here's the APALS system. It's about 17 meters long. It's pretty compact. The front end, the short pulse front end is here. The pump front end sits over there, and the high energy sections sit over here. And again, pump laser produces about 2 kilowatts of average power, and the petawatt laser produces about 300 watts of average power. So where are we with this? There's several commissioning steps here, and we're almost done with commissioning the pump laser actually, so I'll show you that in a minute here. And we're starting with a short pulse commissioning here before the laser actually gets delivered then to the Czech Republic. We have commissioned the front end. Energy stability is one of the main requirements for this. The total is required to be 0.6% RMS out of a kilojoule class system. The front end has an RMS stability of 0.3%. It's all diode pumped. The pumping of the main amplifier is done by laser diode arrays, which have been built in collaboration, have been built by LaserTel in collaboration with us, and we refer to them as HiLads. Those are the most powerful laser diode arrays in the world. Each of them delivers about 250 joules per pulse at 10 hertz repetition rate, but you can also run them faster. We ran them already to 20 hertz. And one of the biggest things for that is actually the drivers, the electrical drivers, which were not commercially available and also were developed by us. Here's how they look like. They're very compact. They provide about 12.5 kilowatt, high currents up to 1,000 amps per pulse. This is how it looks like. This is, this crate here is about the size of a computer rack. Can drive up to 100 hertz or so. We drive it at 10 with 45,000 amperes per pulse. This is, how the laser diodes actually perform. This is from a megawatt array. This is the near field image, this far field image, and this is the pump light distribution at the amplifier, which is excellent and is exactly what you need. Here's where we are with ramping. We have accomplished our phase 1 ramping milestone, which was 60 joules. We actually got 70 joules out of the system. We converted this to 40 joules. And we ran already the diodes, which total of 3.2 megawatts at 10 hertz. So when we started this project, this is how the room looked like. This was about a year ago in summer 2014. And now I'm going to show you how it looks today. I'll try to get something. where the pump laser front is coming together. Here's the short pulse front end coming together. We also bought commercial technology where it was available. This is a 2-joule green laser from Cutting Edge Electronics. And this is where the power amplifier of the pump laser comes together here. You can see the diode arrays here. There's one of them here. Sometimes you see them pulsing. So this is a kilojoule at 10 hertz just out of the diode arrays here. This is one of the power supplies. Very compact if you compare this with a capacitive bank and a flatland pump laser. Very sophisticated control system, of course. Every pulse is the permissive of the next one. So it was pretty amazing to see this grow in 1 year. So with this, actually, the emerging generation of high-energy diode pump lasers could transform a wide range of applications, of course. It is applicable to a lot of other areas. The pump laser in a nanosecond regime now with joules or kilojoule output power. We have designs up to 30 kilojoules and 100 kilowatt solutions. Hopefully, will actually transform some of these applications which are depicted here. And with that, I'd like to end.